In this video, we're going to define work in terms of physics. So work, which is symbolized with a W here, a capital W, is a force applied through a displacement. So force times a displacement, or more specifically, a parallel force times a displacement. And sometimes this displacement is D, and sometimes some texts you'll see this is written as a S. So a force, a parallel force applied through some displacement there. So if we have a force going off like this, let's say this is the force here, and we have some displacement off in this direction. We'll call this our displacement D. And we have some angle between the force and the displacement. We'll call this angle here theta. Then the component of the force which is parallel to the displacement would be right here. And we could find this, this would be F parallel is equal to F cosine theta. And so then the work would be equal to the parallel force times the displacement there, which would be equal to F cosine of theta times the displacement, or F cosine theta times the displacement written as a S there. So this is the definition of work. It's the parallel component of a force times the displacement that the object undergoes. So an object must be moving for work to be done. You can push against a wall or something, you can push against it all day long. You can get really tired at the end of the day, but no work was done unless some displacement occurred. So there must be some displacement, and there must be a force causing this displacement. So if we look over here in this first figure, we have this guy pulling a kid in a cart, and he's pulling kind of upwards at an angle a little bit, and he has a force of 50 newtons, and he's pulling at an angle of 30 degrees, and the cart displaces 30 meters off in this forward direction here. I'll give a sign convention, a positive x being to the right, positive y upwards. So the work done by this guy on the cart here would be the component of the force parallel to the displacement times that displacement. So we have a positive force and going up and to the right. The parallel component is positive. So we have the work done by the man on the cart. We'll say work done by man on the cart is equal to the parallel component of the force. So this is 50 cosine of 30 times the displacement, which was 30 meters. And so this is equal to, I believe, 1,299. And the units of this, the units of work are, we have newtons times meters. So Newton meters, but we don't refer to them as Newton meters. We have something later on that we'll have units for this, and so we actually call this a joule. So a Newton meter is something called a joule after James Joule. So we symbolize this with a J. So the units of work are joules, symbolized by J, and it's their parallel force times your displacement. If I were to, so we have to be very careful here. What is doing work on what? This is the work done by the man on the cart. We had some positive component of the force, and we had some positive displacement. If I were to flip this around, however, and we were to say, well, what is the work done by the cart on the man? So we would have, here's our force that the cart exerts, which would also be 50 newtons via Newton's third law. And so we could say that the work done by the cart on the man, this is going to be, let me do this over here. The work done by the cart on the man is going to be our parallel component of the force, but this is going to be over in the third quadrant, right? And actually, if we put this in standard position, this would be, if we have 30 degrees here, that'd be 30 degrees down below. So it'd be 180 plus another 30, we have 210 degrees. So this is going to be, the magnitude of that force is still 50 newtons. So 50 cosine of 210, which, by the way, the magnitude of that will be the same as the cosine of 30, just in the negative direction. And then times our displacement, which was a positive 30. And so this would be equal to negative 1,299 joules. So we have to be careful what is doing work on what, because we can have a negative work anytime that our displacement is in the opposite direction of the force, then we'll have a negative work. If we have a positive force and a negative displacement, we'll have a negative work. Similarly, if we have a negative force and a positive displacement, we'll also have a negative work as well. So work can be positive or negative. Basically, if the direction of the force and displacement are the same, it's positive. If they're opposite, it's negative. So a couple more examples. Over here, we have this guy pushing. If we look over here, we have a guy pushing on the lawnmower, and he's pushing down like this. There's some component of the force which is parallel to the displacement. The displacement is just off in the positive x direction here. And so the work done here would be the force times cosine of theta, so the parallel component of the force times their distance there. This next figure here, actually, if we look at figure B, then this guy just standing here holding a briefcase. If he's just holding it, so there is no displacement, then the work here is equal to 0. So because the displacement is equal to 0, the work is equal to 0, similar to that pushing on a wall example. Also, though, if the displacement is off in the positive x direction and our force is perpendicular to this, then we would not have any work done there as well. Although, the guy can walk around with a briefcase all day long, it might seem like there's work being done, but in physics, we would say no work is done here because the force is perpendicular to the displacement. If we would have, for that, in example C here, the work done by the man on the briefcase, in C, this is equal to the force times the cosine of the angle between the force and the displacement. So that is 90 degrees if they're perpendicular, times their displacement. But the cosine of 90 is 0, and so the entire work is equal to 0. So no work is being done there. Similarly, if we were taking a briefcase up the stairs here, if our displacement is kind of this direction, then the component of the force perpendicular, we would say, break this up into components. The component of the force parallel, we have F cosine theta. Theta is the angle between the two times the displacement. Same thing with the generator. Moving it straight up and down, we have a displacement like this and a force applied by this wheel here. Anyway, so work is parallel force times the displacement. Another way we can look at this, if we were to plot the parallel component of the force, so F cosine theta, where theta is the angle between the force and the displacement. If we plot that on our vertical axis and we plot our displacement on the horizontal axis, then the area of this, the units of the area of this, F cosine theta times d, and this area would be the work done. So, if this was a calculus-based physics course, we would see that this is the area under the curve, so it would be the integral of the force over the distance there. Same thing with this one here. We would have this area under the curve, plotting F cosine theta, and the distance here. This area would be the entire work done. So a couple couple of quick examples. And actually, before we go into that, let's go a little bit more on this figure C over here. Let's talk about uniform circular motion. Let's say that we have an object going around in a circle like this. Let's say we have a rock tied to the end of a string going around. And so here's our string here. Then we know that the velocity at any point is tangential. So this is our velocity here. So our displacement at this moment would be in the direction of the velocity, right? Because displacement is the same direction as velocity. Yet if it is going in a circle, if it's going in uniform circular motion, so at a constant speed, so that way we have, this is v over here, same magnitude but different direction, then we know that our acceleration is centripetal towards the center. And so then the force that is causing this acceleration is the tension in the string. And so this is our centripetal force, Fc. And so we see that these are perpendicular, right? The centripetal force, the tension in the string, is perpendicular to the velocity. And this will always be true. If we have it over here, our force is this direction, which again is perpendicular to our velocity, so therefore perpendicular to our displacement. So the amount of work done by a string when we have a rock attached to the end of the string and it's going in a circle here is equal to 0, because the force is always perpendicular to this velocity. So the work done by the string on the rock, in this case, is equal to 0 because, we have our theta, the angle between the force and the displacement, is equal to 90 degrees always in uniform circular motion. So there's actually not any work done by the string in uniform circular motion because the force is perpendicular. Lastly, let's just kind of emphasize a little bit more, what's doing work on what. Let's just do a quick little example. Say we have this box here. This displaces to the right 0.8 meters, and we apply this force this way, 120 newtons this way, frictional force 5 newtons back to the left. We also have a normal force going upwards and a weight going downwards. And so if we look at the work done by the force, capital F, this 120 newtons on the box, giving a sign convention here, which I can do without the sign convention, since I know that displacement is off to the right, force is off to the right as well. It's going to be a positive work. But the work done by the force on the box would be this 120 newtons times the 0.8 meters, because the entire force is parallel here. So this is equal to 96 joules of work. If we look, though, at the work done by friction on the box, then this is going to be equal to, this frictional force goes off to the left, right? So this is a negative 5 newtons times, it still displaces to the right. I mean, we can obviously have frictional forces acting opposite displacement always, right? So the work done by friction on the box would be negative 5 newtons times the 0.8 meters here. And so this is equal to a negative 4 joules. So then we can say the net work done on the box, so we'll say W net, this is equal to the sum of all the works done on the box. And so this is going to be our 96 plus a negative 4, and we have this is equal to 92 joules of net work done on this box. So we can find our net work by summing the individual works, or we could have just found this is the same thing. The net work is the sum of all the individual works, or this is equal to the sum of the forces, the net force, times the displacement here. So the net force would have been 120 to the right minus 5 to the left, so we have 115 times the displacement is 0.8. And so this is equal to 92 joules as well. So two different ways that we could get the net work done on this box. And as we see in later videos, this net work will change the energy of the box. And so we might want to consider all the different works being done. So just to summarize here, the work is the component of the force parallel to the displacement. You could write this as a D or an S. And the parallel component of the force will always be the magnitude of the force times the cosine of the angle between the displacement and the force. So theta is that angle times our displacement here. And this is our definition of work.